Welcome back to Dr. MGR Learn Smart Physics Lecture Series. Myself, Dr. M. Sundareshwari, Professor, Department of Physics, Dr. MGR Educational and Research Institute, Madurai, Chennai. In continuation of our earlier session on superconductivity, let us discuss the Bcs theory in this session. What is Bcs theory? It is nothing but a model proposed by three scientists, namely Bardeen, Cooper and Scherfer in the year 1957 in order to explain the reason for infinite electrical conductivity exhibited by superconducting materials at ultra-cold temperature, for which they have been awarded with the Nobel Prize in the year 1972. This slide outlines the development of Bcs theory, such as what are the clues to propose the theory, how to visualize the solid, electron-phonon electron interaction, what are Cooper pairs, how are they formed, how they move in quantum fluid of positive ions and contribute to infinite electrical conductivity, and what are phonons, at what temperature the formation of Cooper pairs is favorable, what are the major accomplishments of Bcs theory. Experimentalists observed a lot. They got the clues from the properties of superconductors and mainly from the following: say isotope effect, according to which Tc into m power half is a constant. Tc is the transition temperature and capital M is the mass number of the given superconducting material. Since here mass of the atom is involved, it is clear some of the positive ions contribution is also involved in the phenomenon of superconductivity. This is the first clue. Moving on, consider the entropy. Entropy refers to degree of disorderedness of the given system. This entropy value is found to be less for superconducting material than that for normal conducting material. That is, superconducting state is a more orderly state. This is the second clue. Third one is that the specific heat capacity calculation indicates that an energy gap is also involved. With these in mind, let us try to understand their model. Before discussing the electron-lattice electron interaction, let us refresh about what is meant by a lattice in a solid. Crystal lattice refers to the regular periodic arrangement of atoms or group of atoms in the three-dimensional space. In the below diagram on the left-hand side, there are two types of circles shown, one in red color and the other in blue color inside the solid lattice. Red color represents the positive ions. Here, positive ions means not only the nucleus, but the nucleus surrounded by the core electrons of the atoms of the given material. These electrons are tightly bound to the nucleus. Then, the blue color represents the valence electrons, the outermost electrons that are loosely bound to the nucleus. Hence, they can wander freely inside the lattice like molecules of a perfect gas. They may undergo collision with themselves or with the lattice, which are elastic. Along with this, you assign the quantum concepts such as wave-particle dual nature, superposition, entanglement, etc. to the lattice. Now, entanglement refers to the correlation between two or more number of atoms, whatever may be the distance between them. With this prerequisite, now we will be able to understand better the electron-lattice electron interaction. Now consider the electron-lattice electron interaction. Here in the below diagram, we have two arrow marks in the left-hand side and two arrow marks on the right-hand side. The left-hand side is for electron 1 and the right-hand side is for the electron 2. In between, we have a wavy pattern that connects two positive ions. So in the lattice, entire lattice, here we are going to consider only a sample with the two positive ions and two electrons. Okay, now with this, we'll proceed like this. Consider an electron 1 with a wave vector k1 is passing closer to the positive ion in the lattice, that is on the left hand side, due to electrostatic attractive force between them. The electron 1 interacts with the positive ion, transfers some of the energy to the positive ion, thereby the lattice is getting distorted. The electron 1 after that gets scattered with k1 minus k wave vector. Now here it should be noted that the lattice vibrations are quantized in terms of phonons. That wavy patterns are the lattice vibrations. Phonons are charge carriers for the lattice vibration. Now the distortion in the lattice is in such a way that it enhances the positive ion density around the distorted place. Means the deformed lattice is advantageous to us because it increases the positive ion density. If you have a doubt how it can increase the positive ion density, let me explain with an example. Imagine that school children are standing in a queue. Suppose if any one boy or girl or a student in between falls down, what will happen immediately? You imagine all the other boys or girls will be coming to the boy who has fallen down in a way to help him or to see what has happened. So in this way, the queue is getting distorted or queue is getting disturbed. Therefore, here also, if you believe that, here also you believe that the deformed lattice increases the positive ion cloud. So it is natural that to this positive ion cloud, another electron 2 with a wave vector k2 comes closer, interacts with the positive ion and gets scattered with k2 plus k. Now, the energy of the second electron is found to be lesser than the energy of the first electron. This shows that the type of interaction involved between the two electrons is an attractive interaction. That is, it could be stated that the two electrons are interacted attractively through phonons because normally we know there will be a Coulombic repulsive force between two electrons in a vacuum. Now here the two electrons, electron 1 with a wave vector k1 minus k and electron 2 with a wave vector k1 plus k, they have interacted attractively through the phonons. Without the phonons, this attractive interaction is not possible. So, these two electrons are forming a bound electron pair called as Cooper pair. So, in the electron lattice electron interaction, the electrons will not be fixed and they try to move into opposite direction, but their correlation or coupling persists over a maximum distance of 10 power minus 6 meter. This distance is called as the coherence length. This is nothing but our entanglement, like your teeth and a cup. Okay, like that they will move one after the other. Now here you can visualize the formation of the Cooper pair. Cooper pair is nothing but two electrons with equal momentum and opposite spin. The left hand side electron, the spin is in the downward direction, and the right hand side electron, the spin is in the upward direction. So these two electrons form a pair through phonons, and the charge on the Cooper pair is 2e, where e is the charge of the electron. These two electrons in the Cooper pair, they are bound to each other or they are coupled with each other. In the previous slide, you have seen the formation of only one Cooper pair, is it not? Now imagine such Cooper pairs are forming throughout the entire lattice, and the volume of one Cooper pair is in such a way that it can encompass 10 power 6 other Cooper pairs in it. Such a dense cloud of Cooper pairs drift cooperatively throughout the lattice of the given solid. Cooperatively means either they are at rest or they will move with identical velocity. In the next slide, you can visualize the animation that shows how the Cooper pairs move flexibly in the quantum fluid like fishes moving in water. Thus, superconducting state is a more ordered state of conduction electrons. Since the density of Cooper pairs is quite high, even for a large current, a tiny movement of such Cooper pairs is enough, is it not? The identical velocity combined with their precise ordering reduces the collision of Cooper pairs. So, there is no collision, no loss in energy, hence no change in electrical resistance. Hence, coherence nature of Cooper pairs and their orderly movement leads to vanishing electrical resistivity, thus giving rise to infinite electrical current, often called by the name supercurrent. This slide shows the coherence length which is of a distance of 10 power minus 6 meter, and also you can see the distance between two adjacent positive ions is only 0.1 to 0.4 nanometer. Let us discuss the energy of in superconducting state. The energy of the pair of electrons in the paired state is found to be less than that in the unpaired state. This difference in energy is called as the binding energy of the Cooper pair, which will be of the order of 10 power minus 3 electron volt. This energy gap is different from the band gap that normally one refers in the band theory of solids. Therefore, superconducting state is favorable only when the temperature of the material is maintained less than the critical temperature or the transition temperature. If the temperature exceeds the critical temperature, the Cooper pairs will be getting dissolved and you will get the normal state. What are the success of Bcs theory? It explains the Meissner effect, coherence length, penetration depth, flux quantization, zero resistivity and energy gap parameter. It has solved the problem of electron energy when there is attractive interaction and gives the expression for transition temperature known by the formula Macmillan's formula. Let me conclude the today's session with a small note on John Bardeen. He has received the Nobel Prize 2 times, one in the year 1956 for the discovery of transistors, the major component of today's solid-state devices and the information technology. The other one will be the 1972, the superconductivity Bcs theory. Well, thank you for listening patiently. All the best.